Hello everyone, Mr. Hine, and today we're talking about local linearization, which is a very awesome tool that was definitely used a lot more in the past than we use it now, but the approach we take to this is still used in higher levels of math because they don't have the tools yet. And you guys see by the end of this video why this isn't used as much anymore, but it's still a good tool to use to approximate values. So let's look at through an example, and let's say we have the function x to the third here, and I kind of zoomed in on part of the graph in a way. And let's say we want to evaluate the function at 3.451. We want to know where's the value at, where's the curve at that point. Now, in today's world, we have calculators that we could just plug that into x to the third and they can calculate it for us. But this was really big back in the day when there weren't calculators, when people had to work things out with their sense of numbers and just how different algorithms work, how addition, subtraction, multiplication, division works. All right. Now, how did they get 3.451? Was they would approximate the value. And how they do that is they use the secant line. So we do it through the use of a secant line. And remember in the previous video, we just talked about what a secant line is, where a secant line is a line that goes through 2 points. Now, we don't know necessarily what the function is at 3.451. We just want to know what it's close to. But what we can do is we can look at the function at 3 and at 4. So at 3 and at 4. And then at those 2 points, if we connect them, it makes a secant line. And remember, a secant line only hits twice. So I know it might look like it's hitting more, but if you were to zoom in on a graph, because this graph has a slight curvature to it, those 2 points would not be hitting anywhere else on the line. All right. And we're gonna use that secant line, and we're gonna find the equation of the secant line, because the equation of the secant line is gonna be very close to what the value is of the function right here. And we'll talk about, maybe this isn't the best one, but you'll see soon. So if we can get the equation of a secant line, then we can approximate the value at that point. So use of a secant line, and then we're going to get the equation of the secant line. To approximate the value. All right, so that's the idea. And we'll go from there. So we have the point here at 3. We're at, so for the equation secant, we need the slope. So we're at 3, 27, because remember the function's x to the third, and the other points at 4, 64. So if we find the slope between those 2 points, that'd be 64 minus 27 over 4 minus 3. 64 minus 27, well, 64 minus 30 is 34, and the 3 is 37 over 1. So the slope between those 2 points is 37. And remember, with point slope form, we could write y is equal to the slope, and then just pick a point, which we'll just do x minus 3 plus 27. So there's the equation of a secant line. That's the equation of the secant line from 3. Yeah, I guess I could just do 3 to 4. That's okay. Now, that secant line, if you notice, is going to very much resemble the curve at that point. Because one thing to notice is that at any point on any curve, if you zoom in enough, it always looks like a straight line, right? If you zoom in enough, it'll always resemble a straight line. Because for a line to curve, it's curving slowly. And if you look infinitely at the minuscule numbers that are happening there, that change is going to be so small where it looks like a linear rate of change. So when we use the equation of a secant line, that's going to give us a good approximation of what the line actually is at that point 3, 4, 5, 1. So we just plug this in now, we can get a good idea, an approximate idea of where our answer is at. So then we have y equals 37, plug in 3.451 minus 3 plus 27. And now this is a lot easier to solve than doing 3.451 to the third, because this is all adding and subtracting numbers just a single time, in which is not too many decimals to work with, and we're not doing too many multiplication. Though this is kind of tricky too, but that's okay. So then we have y equals 37 times 0.451 plus 27. And if you do that, what you'll get, and I'll just use a calculator to get that value, is that the function is about at 43.687. So the function f of 3.451, we're guessing through this approach is 43.687. Now the actual, because we have a calculator now, f of 3.451, let's see how far off we are. The actual 3.451 to the third is 41.099. So you can see that we're pretty close. It's not perfect, but we were close. Now, where are the issues with it and why were we more off than that? Is because to approximate 3451, what numbers did we use? We used 3 and 4. Because remember, I was trying to teach you where this comes from, the history of it. Where 3 and 4 are easier numbers to work with than 3.451. But truthfully, what's going to happen is if we get closer and closer, so instead of, say, looking at 3.3 and 4, what if we looked at, so I'll write it down here. Well, now I'll do it up here. Instead of 3 and 4, what if we did 3.450 and 3.452? If we look at numbers only 1,000th away from 3.451, and we made a secant line there, is that line going to be closer to the actual line that's happening at 3.441? Well, yeah, of course. So that secant line, if we reduce that plus or minus change that we're looking at it, we're going to get closer and closer to the value. So if I were to use those values, it probably would have been pretty close to 41.099. But I was trying to show you more so where it also comes from history-wise, where they wouldn't have chosen these numbers in the past per se, because that's not any easier, in which they would have done 3 and 4 and got an approximate answer. But in today's world, the approach we can use is we can use local linearization to approximate points by picking points that are very close to the actual point we want, and then using a secant line to approximate the value. So that's local linearization. Local because you're making local linearization because we're making a line that's very close to where it's actually at the point. Because remember, if you zoom in enough, it will always resemble a straight line, in which we can find the equation of a line that's very close to it, the points to the right and left of it, and get a good approximation that way. Hope that makes sense a little bit. Very awesome approach. If not, maybe the worksheet will help too. All right, bye-bye.